Today we're going to look at the biggest beauty of quantum mechanics, the time-dependent Schrodinger equation. I've already made a video where I've looked at the time-independent Schrodinger equation, but of course solving the time-dependent Schrodinger equation lets us get the time evolution of a quantum state. In other words, if we put a particle in some system, how does the probability of measuring certain energies in that system change throughout time? And of course, that's the main topic of most undergrad physics courses. The problem, of course, in most of these courses is that you can only study very specific potentials. On a computer, using numerical methods, you can solve for any potential that you want. And that's what we're going to do today. We'll solve the time-dependent Schrodinger equation using two independent methods, and we will verify them by comparing their solutions with each other. Anyways, let's get started on the video.
Rudolph Joseph Alexander Schrodinger. What's going on, bro? Why your name go on forever? You trying to compensate for something that is small? Like the scale of quantum mechanics. That's all I meant,
That's
y'all.
all I meant.
Unable to get pussy, cat in a deterministic state. But your equations were alright. 10 out of 10, mate.
Good job.
We about to solve that time-dependent system two different ways.
Let's
I must
go.
give you some praise. Now let's create some arrays.
So the packages are pretty standard today. We got NumPy, we got Matplotlib for the plotting. Of course, we'll be making an animation with Matplotlib. And we're going to use Numba to do the finite difference algorithm for solving the Schrodinger equation. And then also some SciPy methods for doing the matrix method for solving the time-dependent Schrodinger equation. And I'm also using Science Plots. It's a library that you can install if you like. If you don't want this, or you don't want to install that, I would just comment out this line, but it's also in the Docker image that I've provided as well. So the time-dependent Schrodinger equation, I want to just sort of review the math before we actually get into the coding here. And so this is the form of the time-dependent Schrodinger equation in the position basis. You've probably seen this before. This is the partial with respect to time. You have Planck's constant and all this stuff. And then it's located in a potential, but there's boundary conditions here. And that means that it isn't an infinite square well, right, to an extent, but there's a potential in the middle, right? So even though it's bounded like this, there's a potential in the middle that could be doing whatever. You could have like another sort of well in the center. You could have all sorts of things going on with v of x. The true infinite square well is v of x equals 0 that you're probably used to. And so this equation has a lot of parameters that are kind of a nuisance to deal with, and we don't really want to deal with them, like m and h bar and all that stuff. And we can convert it to a simpler equation to solve mathematically on the computer where we don't have to deal with those parameters. And then at the very end, you can put in those parameters that you want and get the specific situation that you're interested in. For example, maybe you're interested in an electron in a particular well or something like that. L, of course, is the length here of the well. And so what I do is I multiply both sides of this equation by ml squared to get this equation here. And I choose the convention h bar is equal to 1. This is pretty standard, and it sets the units for the problem. So that joules essentially is equal to 1 over seconds, right? This is a convention. And then I also make the transformation. X prime is x over L, t prime is t over ml squared, and v prime is ml squared v. The motivation here is that I have this t in the denominator here, and I have ml squared h bar above. And I absorb that into something like this. Here I have L and X, so X over L is a good dimensionless quantity. And V prime, of course, I'm absorbing all three of these into one constant. And you can check that that just sort of resorts to this equation here when I make all these substitutions for T prime, X prime, and V prime. And so this is a lot easier to solve because there's a lot less parameters that we need to deal with. And so we can solve this equation for X prime and T prime. And we define v prime, and then we make the substitution at the end here. X is L, X prime, T is ml squared. This should be a T prime here and a V prime here. So T prime and V prime. And so we solve it using our dimensionless quantities, and then we can compute whatever quantities we want at the end. But I should note, for all the numerical work, I'm not going to be working with the primes. I'm going to drop all the primes when I'm coding, right? Because it's annoying to carry around these primes everywhere. But you should know that I'm working with the primed quantities when I'm coding. But of course, they're the dimensionless quantities. So there's two techniques we're going to look at today for solving the time-dependent Schrodinger equation. Of course, one is the finite difference method. Now, I'm going over it pretty quickly here today, but if you're curious about how this technique works, I've gone in depth, like really a lot, in my guitar audio video. So I'd look at that video if you're interested in this finite difference technique. It works for any partial differential equation, by the way. And so I make my function, of course, which is a function of x and position and time. I make it discrete on a 2D grid, x being one of the axes and time being the other axis. J is the x and m is time. And I can discretize this function as follows, where j is just an integer and m is an integer. And I have delta x and delta t. So rather than being in a continuous 2D grid, I have a point or a grid of points, essentially. And I make the approximation for the derivative with respect to time, and also an approximation for the second derivative with respect to position. And I get something like this. And what I do is, it's finite difference. What you do is you iterate through time. So at the next time, you use information from the past to get what the wave function is doing at the next time. And you can see m plus 1 is like the future time here, right? And m plus 1 only shows up once. So I could rearrange this equation to solve for m plus 1 quantity here. And I get everything else on the left. So if I know my initial wave function here, all I have to do is use this equation here to solve for the time at m plus 1. And then I go up, and then I use this to solve for the next value. And so this is a finite difference method. Again, it's explained a lot more in my guitar audio video. The second technique is the eigenstate evolution. And this is sort of what you learn in any quantum mechanics course. You separate the time-dependent Schrodinger equation into two equations. And one of them is the time-independent Schrodinger equation that you see here. And this is in the dimensionless form where I don't have m or h bar. So this is the time-independent Schrodinger equation. And so you can solve this, and then your time-dependent equation just becomes, you look for the eigenstates and the eigenenergies that satisfy this equation. So there are only certain energies E and certain functions psi that satisfy this. And there's infinitely many of them. And they're sort of separated apart. So there's this is sort of the quantized stuff in quantum mechanics. And so once you have these eigenstates and eigenenergies, like your eigenvectors and your eigenvalues, you can reconstruct any state you want, psi of xt, is equal to these coefficients Cj times the eigenfunctions psi j, and then you have this energy to Ej, which are the eigenenergies. And the Cj's are the only thing that's unknown here, and you determine the Cj's by looking at the initial wave function here, psi of x0, and you take the integral with respect to psi star of jx. Of course, this is an infinite integral, but because we're bounded in that 0 to L, this becomes a finite integral, and we can evaluate this really easily using a computer. So we'll start with technique 1, which is making the grid. So there's the x-axis and the time axis. And so at any time, you have, of course, your wave function. That's like pressing pause, and you can look at your wave function. In the same way, you can look at only a certain position and how that position evolves with time. So you have your x-axis, your time axis, and your wave function will sort of evolve throughout time. And so the number of points we're going to use in x is 301. So we have 301 points between 0 and L, and we're going to solve for 100,000 different times. 301, you might wonder, why not 300? Why 301? That's to give a nice value for dx here, because if I have 301 points, that's 300 intervals, and so I get a nice value dx. And my dt is 1 times 10 to the negative 7. This is chosen small enough so that this quantity here, which I'll discuss in a bit, is small. X is just creating Lin space here from 0 to 1, and x quantities. That's essentially creating an array. Again, if I were to just look at this, if I import my packages, which I always seem to forget to do. and I look at x, this just creates a bunch of linearly spaced points from 0 to 1. And then I create my initial wave function, which for this purpose of this video is going to be a sine curve, right? And this is actually an energy eigenstate of the infinite square well, where v of x is equal to 0. But in this case, my potential, I'm going to choose a Gaussian well in the center, and you'll see that in a second. So I define my initial state and my Gaussian well, and I can plot the, well, I can make sure that it's normalized, which is what I do here, and that's just choosing by definition so that it's normalized. I can look at this dt over dx squared quantity. This is small. This has to be small for the finite difference method to work, and this is sufficiently small here. And I experimented around with different quantities, and it turns out that this one worked pretty well for this purpose. The potential right here, remember that we're not dealing with a true infinite square well. There's something going on in the center. And so the potential here is v of x is minus 10 to the 4. This is a scaling factor. And this is a Gaussian curve here. So it's 0, and then it kind of, the Gaussian curve is sort of in the center, minus L over 2. So it's right in the center. And it's essentially just a normal curve, which can be expressed more simply as v of x is minus n, n being the normal curve, where mu is equal to L over 2 and sigma is equal to L over 20. And so I can plot our potential, and it looks like this. And so this is what I was talking about. You're bounded between here and here, but your potential, you sort of have this place here, and the particles are going to want to sort of go to the place where the potential is small. The next thing I do is I construct the array psi of xt. Remember, two variables here, so it's 2 dimensions. And so what I do here is I first create an array of zeros with nt and nx. And then my first time, right, because this is the time axis, I set equal to psi 0. So my psi right now, this is the initial state, but everything else is equal to 0, and I have to go through the algorithm, of course, to find for the wave function at all times. And of course it is, this wave function can be complex, as you see, because this equation here involves I, right, which is the complex unit here. And so what I do is I basically take that formula and I code it in here. So this is numba, by the way. Again, I use numba all the time to speed up things because you can use for loops in numba and it runs pretty smoothly. If you were to try to do this just in Python, it would be very, very slow. So I use the numba algorithm to implement the finite difference method. I use complex data types. This is a 2D complex array, so it takes in a 2D complex array and it returns a 2D complex array. So it takes in this psi, and as you can see, like I said, psi right now is not complete. I only have the initial state. And at psi plus 1, it will solve for all these values using the past state. And that's, like I said, that's what this equation is here. It only includes information about the past state with m, and then I use that to find m plus 1, and I do this for all different values of j. And that's what's being done here. So I loop through time, right, because I need to go through all the times to get my wave function evolution. I also loop through all the positions, and my psi t plus 1 I is just the formula that I have above, as you can see. Everything here is just what I have above. And I also have the potential here as well, v I. So it's indexing this array of the potential that I have here. That's part of the finite difference method. And then as I go through this algorithm, you should note that the wave function also needs to be normalized, right? And so I also enforce the fact that it's normalized. So this is like a scaling factor here. And once I compute the next state, I actually normalize it, because sometimes you can have rounding errors and stuff that create the wave function to get bigger and bigger and bigger, so it becomes unnormalized. And this is just something I do to ensure that it stays normalized the whole time. And so what I do is I use this function to compute psi at all times. And this is method 1, so I label it psi underscore method 1. And it takes very quickly to run with numba. And what I have now is my wave function at time 0, the next time, the time after that, right? And so I have an array of, along this axis is x, and the other axis is t. And I can plot some values here. For example, I can plot at m equals 10,000, and note that the real time is t is m times delta t. And I said that delta t is 1 times 10 to the negative 7, and m is 10,000 times 1 times 10 to the negative 7. But remember, this is the dimensionless time as well. Eventually, at the end, I would have to convert back to sort of SI units. And so I can plot, for example, the wave function at this m is equal to 10,000. Of course, my initial wave function And I can also make sure it's normalized, right? So that's what I'm doing in this line. But I can comment this out and I can plot it at a bunch of different times. So this is my initial wave function, at time m is 10, and it will slowly change to become like this. So it starts to squish in there in the center, right? The well is in the center, so the wave function is sort of going to collapse in the center because the particle is going to want to go to the place where there's the smallest potential. So now we use the second technique, and remember the second technique is to solve for all the eigenfunctions and eigenenergies of this system, and then use those to construct the time-dependent state. And I talked about that earlier in the video. And so the first thing we need to do is we need to solve the time-independent Schrodinger equation. And I have a video on that as well. I'll put a link in the description to that. And I've already solved the 1D time-independent Schrodinger equation. So everything I do in this video is based on that video. And I go into depth about setting up that problem appropriately, but I'll go through it quickly here. And so I need my grid in X. Remember, I'm just dealing with X now. This is time independent. I have dx, again, 301, because 301 points gives me 300 intervals. And I specify my initial state, and then I also have a function that gives me my potential. So everything here is very basic. Again, I put a link to my YouTube video here where I go over this problem, the time independent Schrodinger equation. And that essentially involves solving a matrix equation, a tridiagonal matrix equation, and it's an eigenvalue equation. And so I do that here in these 3 lines, but I have an entire video on that, of course. But I need to make sure that this is not L, this should be 1, since L is equal to 1. And so now I have my eigen energies and my eigenvectors. And then I can construct the time-dependent state using this formula here, right? So I know all of these because I've solved them here, right? I can look at them, for example. So v dot t 0, this would be my first energy eigenstate, and I can actually plot it next to x. And I need to make sure that I go like this because, of course, the way I solve it here is I don't include the first and last point because they're both equal to 0. Again, that's discussed in this video. And I have my first energy eigenstate, my second energy eigenstate, and you can see that it sort of looks like the infinite square well, but of course it's a Gaussian well, so it's not going to be exactly the same. So I have my energy eigenstates, psi j. I also have my energies that are given in this w vector. And a lot of them are negative, and then there's also some positive ones. The negative ones, of course, is because the particle is bounded in that potential well. And so those are given by W. And so I have the energy eigenstates, I have the energies J. I just need the coefficients Cj that are given in this formula here. And so I extract my EJs, which are just go through the W array. And I also extract my energy eigenstates psi j as well. And to do that, I take my v dot t and I pad them with zeros, right? Because remember, I don't include the 2 endpoints, again, discussed more in this video, because they're both equal to 0, but I re-put the 0 at the end of both of those v dot t's here. So for example, what I'm doing here is if I just look at this, it has all my energy eigenstates, but I'm not including the first and last point. In order to put a 0 and a 0, because of course that's the boundary conditions of this problem, I can do this np.pad method, and you'll see that that adds a 0 at both the front and the end of every array here. And so the c's can just be solved like this. This integral, of course, just becomes a dot product between these 2 vectors here. And because of the way that the v's are normalized, I don't need to include the dx here. And so this function here is used to compute this formula. There's a clever matrix multiplication that goes on here that's used to compute this formula, and I encourage you to look more into that. But I can do this, and this will get me my psi for the method 2. And using this method, of course, I can plot this wave function at a particular time. And so I can plot both psi naught, which is this blue curve here, and I can also plot the wave function at 10,000 times dt. Of course, this is the probability density because I'm squaring the wave functions here. And so you can see again, like the other, like method 1, it wants to converge into the center because that's where the well is. So we've computed the evolution of the wave function using 2 different methods. What we can do now is we can create an animation that shows, are the 2 methods consistent? Ideally, of course, they'd give the same result, right? We're using 2 different things to solve the same equation. So it's a good way to check this in an animation. And so what we do is we plot the wave function at a particular time on a plot. And then we, in the animation, we evolve time and we see how the wave function evolves as a function of time. And so that's what this function here does. And so that code takes about a minute or so, maybe more like 5 minutes or so to run. And of course you get this beautiful animation here of what's going on with the wave function. And so there are 2 methods, method 1 and method 2. Method 1 shown in red and method 2 shown like this. I plot the potential as the label for the plot here. Of course, the y-axis is the probability density function, and you see immediately it collapses into the center. Remember that the Gaussian well is in the center here. And you can see it sort of moving around, and it's very non-intuitive, right? I mean, remember that this is the probability density function of finding it at a particular position, and so sometimes it's more likely to be out here. Sometimes you get these huge spikes of finding it in the middle, but it immediately collapses, and you get this sort of behavior. But ultimately, the best part about this is you see that using 2 completely different methods to solve for the wave function as a function of time, you do indeed get the same thing. So it shows that both methods are likely doing the same thing. So this is wonderful. And I encourage you to take this code, by the way, and try putting in your own potential, right? You could put a Gaussian barrier in the center too, and you could see what happens. You could put all sorts of things, right? I mean, because this is numerical, you have options to do anything. And you could check that the 2 methods are the same, and then you could be confident. Now, the issue sometimes is if your potential is too narrow, you run into numerical issues if your grid spacing isn't fine enough. And especially for the finite difference method, you have to be very careful of that dt over dx squared. Again, you'll see that in the code. But anyways, this is the animation here, and so this is very neat. So we'll look at one final thing here, and this is something that always sort of confused me as an undergrad, but I think it's important to go through. And that's that we used h bar equals 1, which is sort of weird, right? Especially if you're not used to this. Well, how do we get things back in standard units, right? How do we go from, all this plot here with these various labels? How do we get them to SI, right? Because of course, this is dimensionless here, but in SI, this on the left-hand side is not dimensionless. And what we do is we multiply by h bar in various ways to make things dimensionless, right? If this is dimensionless on the right-hand side, we need to multiply by h bar appropriately to get this dimensionless. And so we'll start with the potential, right? The potential ml squared v is equal to this, and everything here is dimensionless, right? The right-hand side is dimensionless. And we want to therefore make the left-hand side dimensionless. And you can check that the current SI units of the left-hand side are joules squared seconds squared, right? And because h bar has units of joules seconds, we thus need to divide the left-hand side by h bar squared. And so we get the following equation here, ml squared divided by h bar squared v is equal to this. We don't have to do anything to the right-hand side because h bar equals 1, right? You can always multiply by 1 or divide by 1. And so we get this here. In other words, the potential v of x, the dimension full, right? This is the true potential with its units in SI, is equal to this quantity here. Minus 10 to the 4 h bar squared divided by ml squared times this dimensionless, of course. This is just the normal Gaussian curve. We can do the same thing for time. Remember that the time shown on the plot here, you have time, blah, equals some number, and I call this number a here. So time equals a. And we know that a is dimensionless, but the left-hand side is not dimensionless. It turns out that the left-hand side actually has dimensions of joules inverse seconds inverse. And in order to make this dimensionless, h bar having units of joules seconds, we multiply the left-hand side by h bar, leading to this formula here. Remember, h bar equals 1, we can multiply by 1, that's fine. We get this formula here. In other words, solving for time, we get time is equal to this factor here times a. So if we're curious what the true time is in this plot, right, we look at this number. To get the true time in SI units, we would take this number, a, and multiply by this factor out front. And so in conclusion, if you tell me what m and l are, maybe you're interested in an electron in like sort of an atomic radius type sort of problem here with L, then all I need to do once you tell me m and l is I plug those into this here on the plot, and I can tell you what the time is, and I can also tell you things about the position as well. Anyways, I hope you enjoyed this video. We went through it very quickly. I encourage you to go slowly through the code. If you're interested in this, again, it's on my GitHub. There's a link in the description of this video. If you did enjoy, please remember to like and subscribe, and I'll see you next time.